Hello and welcome back to Steven Data. In the last video, we talked about the advantages of statistics in data science and learned how statistics helps data scientists to drive insights from a bunch of messy data. Now, it's time to officially start learning probability and statistics. In this video, we are going to talk about two main subjects of statistics called random experiment and sample space. We are going to understand their definitions and see how these two can help us modeling our real-world problems. Okay, enough talking. Let's dive into the video to see what we can get from these two terms. Before giving the definition of random experiment, let's see an example, shall we? If we measure the current in a thin copper wire, we are conducting an experiment. However, day-to-day repetitions of the measurement can differ slightly because of small variations in variables that are not controlled in our experiment, including changes in ambient temperatures, slight variations in the gauge, small impurities in the chemical composition of the wire, and current source drifts. Consequently, this experiment, as well as many we conduct, is said to have a random component. In some cases, the random variations are small enough relative to our experimental goals that they can be ignored. However, no matter how carefully our experiment is designed and conducted, the variation is almost always present, and its magnitude can be large enough that the important conclusions from our experiment are not obvious. Our goal is to understand, quantify, and model the type of variations that we often encounter. When we incorporate the variation into our thinking and analysis, we can make informed judgments from our results that are not invalidated by the variation. Models and analysis that include variation are not different from models used in other areas of engineering and science. For example, a mathematical model or abstraction of the physical system is developed like this figure. It doesn't need to be a perfect abstraction. For instance, Newton's laws are not perfect descriptions of our physical universe. Still, they are useful models that can be studied and analyzed to approximately quantify the performance of a wide range of engineered products. Given a mathematical abstraction that is validated with measurements from our system, we can use the model to understand, describe, and quantify important aspects of the physical system and predict the response of the system to our inputs. Until now, we discussed models that allow for variations in the output of a system, even though the variables that we control are not purposely changed during our study. But now, let's assume we have this figure that graphically displays a model that incorporates uncontrollable inputs or noises that combine with the controllable inputs to produce the output of our system. Because of the uncontrollable inputs, the same setting for the controllable inputs do not result in identical outputs every time the system is measured. For the example of measuring current in a copper wire, our model for the system might simply be Ohm's law. Because of uncontrollable inputs, variations in measurements of current are expected. Ohm's law might be a suitable approximation. However, if the variations are large relative to the intended use of the device under study, we might need to extend our model to include the variation. As another example, in the design of a communication system, such as a computer or voice communication network, the information capacity available to serve individuals using the network is an important design consideration. For voice communication, sufficient external lines need to be available to meet the requirements of a business, assuming each line can carry only a single conversation. How many lines should be purchased? If too few lines are purchased, calls can be delayed or lost. The purchase of too many lines increases costs and it's not efficient. Consequently, design and product a model to find the sufficient number of lines is required to meet customer requirements at a competitive cost. In the design of the voice communication system, a model is needed for the number of calls and the duration of calls. Even knowing that, on average, calls occur every 5 minutes and they last 5 minutes is not sufficient. If calls arrived precisely at 5-minute intervals and lasted for precisely 5 minutes, one full line would be sufficient. However, the slightest variation in call number or duration would result in some calls being blocked by others. You see how this variation can make our job hard in order to model the behavior of a variable. But don't worry, we always have a solution to deal with such nasty problems. Now, it's time to give you the definition of random experiment. An experiment that can result in different outcomes, even though it is repeated in the same manner every time, is called a random experiment. Now, it's the moment to spend our time with sample space. To model and analyze a random experiment, we must understand the set of possible outcomes from the experiment. In this video, I use the basic concepts of sets and operations on sets, and I assume that you are familiar with these topics, but if you don't get afraid. You can ask your question in the comment section and I will answer them with honors. Let's see what is the definition of sample space. The set of all possible outcomes of a random experiment is called the sample space of the experiment. And it's worth mentioning that the sample space is denoted as S. A sample space is often defined based on the objectives of the analysis. The following example illustrates several alternatives. Consider an experiment that selects a cell phone camera and records the recycle time of a flash. I mean, the time taken to ready the camera for another flash. The possible values for this time depend on the resolution of the timer and on the minimum and maximum recycle times. However, because the time is positive, it is convenient to define the sample space as simply the positive real line like this. If it is known that all recycle times are between 1.5 and 5 seconds, the sample space can be like this. If the objective of the analysis is to consider only whether the recycle time is low, medium, or high, the sample space can be taken to be the set of 3 outcomes, which are low, medium, and high. If the objective is only to evaluate whether or not a particular camera conforms to a minimum recycle time specification, the sample space can be simplified to a set of 2 outcomes, which are yes or no, and that indicates whether or not the camera conforms. As you may have noticed, we have 2 types of sample space, discrete and continuous. A sample space is discrete if it consists of finite or countable infinite set of outcomes. On the other side, a sample space is continuous if it contains an interval, either finite or infinite, of real numbers. In our example, the choice of S equals to positive real numbers is an example of a continuous sample space, whereas the S, which has 2 outcomes of yes or no, is a discrete sample space. As mentioned, the best choice of a sample space depends on the objectives of our study. To clarify my last sentence, let's see another example. Suppose that the recycle times of 2 cameras are recorded. The extension of the positive real line is to take the sample space to be the positive quadrant of the plane of S, which is equals to R plus in R plus. If the objective of the analysis is to consider only whether or not the cameras conform to the manufacturing specifications, either camera may or may not conform. If the ordered pair YN indicates that the first camera conforms and the second does not, the sample space can be represented by the 4 outcomes of yes, 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 no, no, yes, And finally, no, no. If we are interested only in the number of conforming cameras in the sample space, we might summarize the sample space as this. As another example, consider an experiment in which cameras are tested until the flash recycle time fails to meet the specifications. The sample space can be represented as no, yes, no, yes, yes, no, yes, 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 no, and so forth. And the last one is an example of a discrete sample space that is countably infinite. There are other ways that we can show a sample space, such as using tree diagrams. When a sample space can be constructed in several steps or stages, we can represent each of the n1 ways of completing the first step as a branch of a tree. Each of the ways completing the second step can be represented as n2 branches starting from the ends of the original branches, and so forth. But before wrapping up the video, let me give you an example of this tree diagram too. Imagine each message in a digital communication system is classified as to whether it is received within the time specified by the system design. If 3 messages are classified, we can use this tree diagram to represent the sample space of possible outcomes. Each message can be received either on time or late. The possible results for 3 messages can be displayed by 8 branches in the tree diagram like this. So, to wrap up the video, let's review again what we have learned about 2 common terms in probability and statistics. First, we learned that in real-world problems, there is always variation that can affect our conclusion. So, in our modeling process, we should take account of it to make fair judgments about our experiment. Then, we learned that all these experiments that can lead to various results, even though they are repeated in the same manner every time, are called random experiments. After that, we learned how to model and analyze a random experiment. First, we must understand the set of possible outcomes from the experiment. In other words, we should know some information about its sample space that is formally defined as the set of all possible outcomes of a random experiment. And that is done. Congratulations! Now you can understand 2 important terms in probability and statistics. And undoubtedly, knowing these 2 is essential in order to understand probability properly. If you have a question about the terms I was talking about or anything related to statistics and probability, please don't hesitate. Comment it in the comment section and I will answer them as soon as possible. Finally, if you liked the video, please hit the like button, and if you are interested in this type of topic, please consider subscribing to this channel because it keeps me motivated to create this type of content. I hope this video helps you a lot, and until then, happy learning!